Good afternoon. Welcome to the fourth lecture in a series of lectures on field and Galois theory. Today, Adrita will be talking about fundamental theorem of Galois theory. Adrita, please start.
Okay. So, in our last talk, we had discussed about the definition of Galva extensions, and we had given 4 equivalent statements for an extension to be Galva. And today we will be stating the final equivalent condition, that is the fundamental theorem of Galva. What does the fundamental theorem state? It says that if we have this extension m over k, which is Galois, and we denote by G the Galva group. And then we look at the sub extensions. So we have sub extensions L between M and K. And then we have subgroups of the Galva group G. So we have the trivial group, and we have different subgroups between the trivial group and the Galva group G. Then we define two functions. So first we have phi, which maps L to the Galva group of M over L. And then we have psi, which maps a subgroup H to the fixed group, of the field fixed by the actions contained in H. And the fundamental theorem says that if this is a Galva extension, then phi is psi inverse and psi inverse is phi. So these, and psi is phi inverse. So we have this relation if the extension is Galva. So in particular, what we are doing is we are taking L and we are mapping that to the Galva group of M over L, and then we are mapping back to M, and we call this G1, and we are mapping it to the points fixed by this action. Now note that this is a subgroup because all the automorphisms contained in the Galva group of M over L fix L, and when we apply those automorphisms, we know that L is fixed, but there might be other points that can be fixed by the group by these actions. So this is one, and the second mapping that we have is we map the fixed point set, the other way around. We map H to the fixed point set, and then we map back to the Galva group M over MH. And again, note that the subset is obvious because we are mapping it to the Galva group, and the automorphisms that fix M and that fix the group MH are H, but there might be other automorphisms that fix. So the subset property is obvious. Now we want to show that it's not just a subset, they're actually equal. So our question is, are they equal? What we will show is that this equality is by size. Now we will show that they are equal in size. What does size mean? So for the group H, the size of H is the order of the group H, and because they are a finite extension, so the group is finite and we can talk about the order of H. But the size of L is the size of the extension, so the degree of the extension M over L. Now note that we look at the extension M over L and not L over K. This is because the smaller the group, the larger the field. So it's an inverse sort of relation among the size. So if we have a larger sized subgroup, we have a smaller sized subfield. And what we will show, so we need to show two things. So the first equality, that is when we map H to MH, we need to show the order of the group is equal to the extension M over MH. Now this is true because recall that in the last lecture we had given the equivalence condition that if a group is Galois, this is a equivalent condition for the group to be Galois. So this is true since K over M is Galois. And the second equality that we want is when we are mapping L to the Galva group of M over L, we want to show that the degree is equal to the order of the group. So what we do here is the following. So we look at the Galva extension. So first by the property of Galva extension, we look at the extension, the Galva group M over K. And this is equal to M colon K, since we have seen it in the previous lecture that this is a definition for being Galva. And then we use this. So this is equal to the summation of all automorphisms that take L to M, and the sum is of extensions from phi of L to M. And note that the number of such automorphisms is less than equal to L over K, and the number of extensions is less than equal to the degree of M over L. And hence we can just take the multiplication and we get M over L times L over K, which is equal to M over K. So note that we have M over K on both sides. So in particular, both these inequalities are equalities, and this has to be an equality. Now in particular, we will be looking at this equality. So what we have here is the number of extensions from phi L to M is equal to M over L. In particular, we take phi to be the identity element, and hence we get the required equality immediately. So we get M over L is equal to the Galva group of M over M. The order of the Galva group. And this concludes the proof of our fundamental theorem. Next, what we will look at is, we have shown that if extension is Galva, the fundamental theorem follows. Now, the question arises, so what if the extension is not Galois? So what we can write is, we have K, then we have Mg and M. So when it was Galva, we had an equality here, if and only Galva. And G is the Galva group of M over K. So the equality holds if and only if the extension is Galva. So by the fundamental theorem, we know that there is a one-to-one correspondence between the subgroups of G and the sub-extensions of the form K over L over M. But here, what we have is we get a one-one correspondence between subgroups of G and sub-extensions of the form K over L over M. But we have an extra condition here such that the fixed group is a sub-extension of L. So in particular, we get the information here, but due to the fundamental theorem, we do not have any information about groups, about sub-extensions that lie here. So in particular, we have a strict inequality between the number of extensions and the number of subgroups. Now we will look at a few examples. So first, very basic example, we take the real numbers over the complex numbers. And what is the Galva group? The Galva group is trivial. So it's 1 and Z mapping to the conjugate. So we take the extension, we have C, we have R, and notice that we have the identity element group, so the trivial group, and the group containing 2 elements, so the identity and Z mapping to Z bar, so the conjugation. And note that this is the correspondence. So the smaller group corresponds to the larger field. So C corresponds to the identity group and the trivial group, and R corresponds to the group of both, so the whole Galva group. And we know this is an extension of degree 2, and this is a group of order 2. Now we look at another example. So suppose we take Q over Q cube root 2, and this is not a Galva extension because it's not normal. So we add the other root to make it a splitting field and hence a Galva extension. So we have cube root of 2 comma omega. So this is our Galva extension, and the Galva group, so G, is isomorphic to S3. So what is S3? S3 is the permutation group, and we permute 3 elements. So we have cube root 2, we have cube root 2 omega, and we have cube root 2 omega squared. So this is our Galva. Now we look at the map of the different sub-extensions and subgroups. So what do we have for the fields? We have, this is the overall field, and then we have the base field Q. So what are the first 2 extensions? So the first 2 extensions are trivial. So we have cube root 2, then we have Q cube root 2 omega, and finally Q cube root 2 omega square, and these are extensions. Finally, we have an extension here, which is just Q of omega. And for the groups, what we have the trivial group, and we have the whole group S3. And we have 3 subgroups here. So we have 2 comma 3, 1 comma 2, and 2 comma 1 comma 3. Sorry, 1 comma 3, and a final extension which has 1, 1, 2, 3, and 1, 3, 2. So these are all the subgroups. Now note that this is an extension of degree 2, this is an extension of degree 2, and these are extensions of degree 3, and this is an extension of degree 2, and this is an extension of degree 3. Now we look at the order of the fields as well. So this is order 2, this is order 3, and this has order 3, and this is order 2. Now, finally, look at the correspondence. So the larger field has the smaller group corresponding to it, and the intermediate fields have the intermediate groups corresponding. Now note that this is the normal extension. Color. So this is a normal extension. These 3 are normal extensions because they are splitting fields. Again, this is a normal extension, and this is a normal extension. So we have different normal extensions here, and we can see that this extension is not normal because it is not a splitting field, because the because the element omega is not present. Similarly, we can see that this is the identity is normal in all groups. So all these are normal subgroups. So identity is the normal subgroup of all these three groups. And this is the group A3. And we know that this is normal in S3. So this is a normal subgroup. So we have here a correspondence between normal extension and normal subgroup. So the terminology of calling them normal is quite natural. And finally, we can see that the normal extensions and normal fields actually normal subfields, the normal subgroups correspond to each other. The next example that we have is of the finite fields. So these are quite interesting examples, and we looked at all the finite fields and their sub extensions. And in particular, we look at the Galois field. So suppose, for example, we have the field F2 over F16, and the degree is F16 over F2 has a degree 4. So we have the Galva group of order 4. And how do we generate the Galva group? We look at the Frobenius map. So we discussed the Frobenius map in one of our past talks, and the Frobenius map takes A to A squared because the prime here is 2. And so we look at the compositions. So phi squared takes A to the power 4. Phi cube takes A to the power 8. And phi to the power 4 takes A to the power 16. And this is equal to A. So this implies phi to the 4 is identity. So phi generates a cyclic group. So the cyclic group generated by phi is of order 4. So in particular, we can say that the group generated by phi is isomorphic to our Galois group of F16 over F2. So let us look at the extension. The extension is of the form. We have F16 and we have F4, and finally we have F2. And the group correspondence is the group identity. Then we have the group generated by identity and phi square. Finally, we have the group that contains identity, phi square, and phi to the 3. And phi to the 4 is identity, and this is the correspondence between our groups and subfields. And in particular, when we have the group Fp contained in Fp to the n, the Galois group is cyclic and is generated by the Frobenius map phi, which takes A to the power t. So let us look at another example. Suppose we have the group F2 to the power 6. Then we have two subfields, F2 to the 3 and F2 to the power 2, and we have F2 here. And the group structure is the group containing identity. Then we have a group of order 2, we have a group of order 3, and finally we have the group of order 6. So this is all for finite fields. Now we look at a final example. So now we look at the extensions over Q. So suppose we consider Q zeta where zeta to the power 7 is 1. So zeta is the 7th root of unity, which is implies zeta equal to e to the 2 pi I by 7. And in particular, we can break down the polynomial. So we have x to the 7 minus 1, which is equal to x minus 1 times x to the 6 plus x to the 5 up to x plus 1. And this is irreducible by Eisenstein. And so this group is a Galois extension of the, so Q over Q zeta is Galois. And the other roots of this polynomial, so the roots are 1, zeta, zeta square up to zeta to the power 6. These are all the roots. So what is the Galois group? Now we have seen that this is normal because it's generated by a root of an irreducible polynomial and has all the roots. So this Galois, so we had to show two things. We have shown that it is normal, and secondly, we have to show that it is separable. Now it is separable because Q has characteristic 0, and hence any extension over a finite extension of a characteristic 0 field is separable. And normal because of the splitting field. Now we look at the Galois group. So the Galois group is generated by the automorphisms of the form sigma n, where sigma n of zeta is zeta to the n, and n runs from 1 to 6. And what is the group operation? So the group operation is composition. Sigma n compose sigma n equal to sigma nm. And the Galois group thus formed is, so the Galois group is Z mod, 7Z star. And this is cyclic of order 6, because we know that since 7 is a prime, the group of units of Z mod 7Z is isomorphic to the group Z mod 6Z. And here we have the generator to be 3. So why can we write this? So we have a 3, and then we have 3 square, which is 9, and that is 2. Then we have 3 cube, which is 6. We have 3 to the 4, which is 4, and we have 3 to the 5, which is 5, and finally we have 3 to the 6, 7. No, sorry. So this is 1. So 3 is a generator of the group Z mod 6Z. And what we have, since the cyclic group is multiplicative, now we look at the subgroups. So the subgroups that we have here are the following. So we have Q zeta, then we have 2 subgroups. So what we have, firstly let us look at the subgroups. So we have identity. We have the group generated by 1 and 6. So recall that 6 was 3 cube. And then we have the group generated by 1, 2, and 4. And finally, the whole Z mod 7Z star. And the group operation is multiplication. So we have here, so note that 6 is, okay, this is degree 3, this is degree 3, this is degree 2, this is degree 2. Now, note that 6 is actually, so 6 zeta to the power 6 is actually equal to zeta inverse. So we have the group here generated by Q and zeta plus zeta inverse. And so we have zeta plus zeta inverse, which is equal to 2 cos 2 pi by 7. So this is the subgroup, and the degree of this is 2. Okay. And finally, we have Q. Now we want to find out this subfield. So what is the subfield? So what is the subfield that lies here? And just like the previous construction, we can write it as Q alpha, where alpha is equal to zeta plus zeta to the power 2 plus zeta to the power 4. Now note that it is a quadratic extension, so alpha must be the square root of something. And let us look at alpha square. So it must be generated by a quadratic. So alpha square is zeta square plus zeta to the power 4 plus zeta to the power 8, which is again 1, plus twice zeta cube plus zeta 6 plus zeta 5. And we can just add and subtract 1. This gives us zeta cube plus zeta 6 plus zeta 5 minus 1. Now again, we can add alpha to it and subtract. So plus alpha minus 1, and this gives us 0 since the sum of the roots is 0. So what we get is minus alpha minus 2. So in particular, we have the equation alpha square plus alpha plus 2. This is 0. And hence we can find out alpha from here is minus 1 plus minus root minus 7 by 2. So we can say that Q of alpha is actually equal to Q generated by root minus 7. So these are all the extensions we have here. We have a degree 2 extension. So this is a degree 3 extension. This is degree 2 and this is degree 3. So this was one of the examples of a field which was over Q, and we saw the finite extensions. Now let us look at another example. So instead of taking cube roots, we will now take the fourth root. So we take Q, we extend it to Q root fourth root of 2, and finally we extend it to the splitting field, which is Q, takes fourth root of 2 and takes the identity I. So okay, so we note that this is degree 4 and this is degree 8. Sorry, this is degree 2. So this is a degree 4 extension, this is a degree 2 extension. So the degree of Q, fourth root of 2 and I, comma Q, this is 8. And what we get is the Galva group should be a group of order 8. And before proceeding, let us look at some obvious sub-extensions. So the sub-extensions that we have here. So sub-extensions of this extension are obviously the trivial ones. So we have Q, the base field, and the whole field. Then we have Q fourth root of 2. Then we have Q fourth root of 2 times identity. Then we have Q root 2, Qi, Q root 2i, and finally we have Q of I comma root. There are a couple more, and we shall see that when we construct the Galva. Now we have the Galva group of order 8. So what exactly is the Galva group? Here we note that we have fourth root of 2 here. We have fourth root of 2 times identity. We have negative fourth root of 2. We have a negative fourth root of 2 times identity. So this is a square. And the Galva group is the group of symmetries of the square. So in particular, it is D4. Sorry, it's D. Yeah, it's D4. So we have the D8. We have twice the number of sides of the polygon, so it's D8. Now it is enough for us to look at the subgroups of the Galva group D8. So instead of calculating it by hand, we will look at it through the subgroup geometrically, and we look at it through the symmetries of the square. So we proceed that. So first we have the obvious trivial group, and then we have the reflections. So suppose this is the square, we can reflect it along the horizontal axis. We can reflect it along the vertical axis. These are two reflections. Then we have the rotation. Okay, so these are all degree 2 extensions. So we have the rotation by 180 degree, and that composed twice gives you the whole group. So this is a degree 2 extension again. Then we have the remaining two reflections. So we reflect it along this axis, and finally we have the reflection along this axis. So these are the 5 groups which are of degree 2. So we have 4 reflections and 1 rotation. And note that these are degree 2 extensions, so these are all isomorphic to Z mod 2Z. So these are all the groups here. And then we have the degree 2, so these are degree 2. Now let us look at degree 4. So the degree 4 is all the symmetries of this rectangle of this form. So we have the reflection here and the reflection here. And then we have the 90-degree rotation. And finally, we have all symmetries of the rectangle of this form. So we have rotation along these two, so reflection along these two axes. And obviously, we have this over D8. These are the degree 4 extensions. So what exactly are these groups? So this is isomorphic to Z mod 2Z cross Z mod 2Z. Again, this is isomorphic to Z mod 2Z over, sorry, cross Z mod 2Z. And this is isomorphic to Z mod 4. So this is the group of order 4, and this is the cyclic group of order 4. All right. Now we see how we can extend these. So this is an obvious extension. So we can have 290 degrees to get a 180 degree. Now these can be extended to these two. This can be extended here. Similarly, this can be extended here, here, and here. So we have all these extensions. Now let us look at the chart for the subfields. So of course, this corresponds to Q. This corresponds to Q 4th root of 2 comma identity. This is okay. So this is the Qi, because 90-degree rotation, this fixes the element I. Then this is Q root 2. This fixes the element root 2. And this is Q of minus 2. Sorry, Q of I root 2. So we have these 3 groups corresponding to these 3 fields. And then obviously we can see this is a reflection. So it fixes Q of 4th root of 2. This is another reflection which fixes this. So we have Q of I times 4th root of 2. And this we can check, it fixes both. So it fixes Q root 2 and I. So we have all the subfields that we had listed earlier, but we can see that there are 2 more fields which we had missed when we listed the obvious subfields. So what are these 2 fields? So here we can see that when we rotate, these 2 get interchanged. So when we reflect, these 2 vertices get interchanged. So the sum remains constant, and we can get that this is the field Q of 4th root of 2 times 1 plus I, and similarly this is Q of 4th root of 2 times 1 minus I. So we have listed all the subgroups, and these give me all the sub extensions. Now note that we would like to see the normal extensions. So note that these 2 are conjugate, and these 2 are conjugate. That is, you have an isomorphism that takes one to the other. So you can take 4th root of 2 to I times 4th root of 2, and you can take the other two reflections. So since they're conjugate, they're obviously not normal. Again, we can see that these are normal. So this is identity. So all these extensions are normal. And this is a normal extension. This is a normal extension. This is a normal extension. And since the rotation and this is the symmetric group, this is the cyclic group. So these are all normal extensions. Again, this is a normal extension. This is a normal extension. But these two extensions here are not normal. So what we get here are the conjugate groups are not normal extensions. And in particular, they are not normal subgroups of the group that contain them. So these are all the subgroups and the corresponding subfields of the extension Q to 4th root of 2 and I. So we finished our group on the fundamental theorem and Galois extensions, and we will conclude with the particular application. So what we do today is the following. So we will conclude with what is called the primitive element theorem. Now, what is a primitive element? A primitive element is an element such that it generates the whole field from a subgroup. So suppose we have an extension, say K over M, and this is a finite extension. So this is finite. And we can write M equal to K times alpha 1, alpha 2 up to alpha n for some number n. Now the question that we ask is M equal to K alpha for some alpha? Now, why do we want this? Because we can just have a single root of polynomial and we can generate, and this gives us a lot of leverage to prove a number of more theorems, and this comes in handy quite some time. The answer in general is no, but it is yes if M is separable. So if we have a separable extension, the extension can be written as a single element, and these extensions, that is K alpha, are called simple. So we look at simple extensions, and what we will prove today is the theorem that says that if M over K is a finite separable extension, then M is simple. That is M equal to K alpha for some alpha. So any finite separable extension is simple, and we shall give the proof of this. So first we look at the simple case. So we look at two cases. The first case is if K is finite. So we look at finite fields, then we know that for a finite field, and then we have a finite extension K. So we have K finite and we have M is a finite extension. So we can write M cross is cyclic. And since it's cyclic, it has a generator, and that generator we can call alpha. So since cyclic implies alpha is a generator of M cross, and we can write M is K alpha. So we can see in the finite case, it's quite easy to show, but we'll have to develop some machinery to show it for the case where it is not finite. for that, we give a lemma. What does the lemma say? That if we have a extension, so suppose we have an extension k over k, which is of degree n, and n over k is a finite normal extension such that k, so this is small k, this is capital K over n is a n contains capital K, then there exists at most n distinct k isomorphisms of k into n. So recall that we had proved this lemma in our last class. So in particular, we had proved it for the closure, but we had given the general case where we can take any field X such that it contains the subfield. Then this extension has at most the number of isomorphisms that fix K in this extension is at most the degree of the extension. So using this, we shall prove our second case. So when we have the second case, then K is, capital K is infinite. So we have, we give the names. We have m over k is equal to n, and n over k is finite normal such that it is in n, and we know that this is separable, so m over k separable. So therefore, there exists n distinct k isomorphisms sigma 1 up to sigma n of k to n. Now let I not equal to j, and we define the set Vij to be all elements x in M. Sorry, this should be M, not M. Okay. So we define all elements x in M such that sigma I of x equal to sigma j of x. So we try to define the fixed field. So we have the fixed field here, and we can see that Vij is a subspace of M. So it's not just a subset of M, it is actually a subfield of M, and we have, since I not equal to j implies sigma I not equal to sigma j, because we have n distinct isomorphisms. So this implies that Vij is not equal to M, but it is a subset. So we can say that union of Vij is not equal to K. Because we know that when we have a finite number of subspaces of vector space, which is of a finite degree, which is of a finite dimension, then the union of all subspaces which are not equal to K cannot be equal to K. And from here, we can conclude. From here, we can conclude. Therefore, there exists alpha in K such that sigma I alpha not equal to sigma j alpha for all I not equal to j. So we get this alpha is in K minus union of Vij, and therefore alpha is the generator, that is M equal to K alpha. And hence we have proved our primitive element theorem. So we look at an example. Look at the following example. So we have K subspace of M, which is equal to M of where, so we take K equal to Q and M equal to K root 2 root 3. So this is an extension, and we can see that this is generated by two elements, root 2 and root 3. And we take this. We take the element x equal to A plus B root 2 plus C root 3 plus D root 6. And we can take the element of the form B, C, D not equal to 0, then x is primitive. So we can have an element which is of the form this, and it is contained in M because it's a field, so we can easily see that this is contained in M. And in particular, any element of M can be written in this form, and we can see that this is a primitive element. Now we have seen that for separable extensions, we can write it in the form of a primitive element. But what about inseparable extensions? So since we have given the proof for separable extensions, we will look at inseparable extensions and we'll see that it need not be true. So what about inseparable extensions? So we take the following example that we had given for inseparable extensions. So take the field K such that characteristic K is P, which is not greater than equal to 0. So we take the P to be greater than equal to 0 because we know that any extension of characteristic 0 is separable. And we look at the following. So we have the field K with two generators. So it's a two variable rational functions with coefficients in K. So this is our field extension. So this is our field, which we, the subfield that we, the overall field that we have. And then we look at the following. Okay, so what do we have here? We have this, and then we look at K of capital T comma capital U, where T is equal to T to the power P and U is equal to small u to the power P. Now we take this to be our K and this to be our M. So we have the extension K over M. Now, if A is in M and A to the power P is in K, then the Frobenius map, that is phi of A equal to A to the P. So this is a homomorphism of field that maps M into K. So what we do, we take M in M and suppose okay, so I think I messed up the notation. We have M subspace of K. So suppose we have we have K subspace. I'm sorry. So we have this extension. Now suppose A is in M and A is the root of x to the power P minus B equal to 0. So B is in K. So this Frobenius automorphism guarantees the existence of such a B. So we can say that A generates a field of degree P. Now K over M has degree P square. So there are no primitive elements, and so there exists no primitive elements. And in particular, we can see that this M over K is a finite extension because it's of the degree p square, but it has infinitely many sub-extensions. And that concludes it for inseparable extensions and also our talk. So does anybody have any questions?
Yeah, I don't think there are any questions. So thank you, Adrita, for the talk. Join us again on 26th June for a talk by Sanchayan Boval of MMath first year. His talk is titled An Unconventional Approach to Groups. Thank you.
Can you make this announcement again, please?
Yeah.
Sir.
So the next talk will be by Sanchayan Boval on 26th June at the same time, 3 p.m. The title is An Unconventional Approach to Groups.